Hello, friends. Before you can really understand calculus, limits, derivatives, integrals, any of it, you need to be completely comfortable with one thing, the coordinate plane. Because in calculus, everything we study eventually shows up as a graph, a curve, a line, a shape on this grid. And if you can't read that picture, the math behind it never really clicks. So in this video, let me walk you through coordinate planes and graphs from the ground up, what they are, how they work, and why they matter. Let's get into it. All right, let's start with the basics. You've already seen a number line, that single horizontal line with numbers spread out on it. That's a one-dimensional space. You can only move left or right. Now a coordinate plane is just the next step up. Take that number line, lay it flat as your horizontal axis. We call it the x-axis. Then add a second number line standing straight up through it. That's the y-axis. The point where they cross is called the origin, written as 0, 0. And just like that, you've gone from one dimension to two. Now you can describe any location on this flat surface using two numbers. Pretty simple, right? Let me show you how. Now here's where the magic happens. Every single location on this plane can be described using just two numbers, written together like this, in parentheses, separated by a comma. We call this an ordered pair. Take the point, 3, 2. The first number is always your x. That tells you how far to move left or right from the origin. The second number is always your y. That tells you how far to move up or down. So for 3, 2, you start at the origin, walk 3 steps to the right along the x-axis, then 2 steps up. That's where your point lives. And here's the key word, ordered. The order matters. 3, 2, and 2, 3 are two completely different points on the plane. Think of it like a street address. House number first, street second. Swap them, and you end up somewhere else entirely. Once you've got this, you've got the whole system. Now look at what the two axes do to the plane. They slice it into 4 regions. We call these the 4 quadrants, and they're numbered 1 through 4 using Roman numerals, starting from the top right and going counterclockwise. So quadrant 1 is the top right, quadrant 2 is the top left, quadrant 3 is the bottom left, and quadrant 4 is the bottom right. And each quadrant has its own personality based on the signs of x and y. In quadrant 1, both numbers are positive. In quadrant 2, x is negative, but y is still positive. In quadrant 3, both are negative. And in quadrant 4, x flips back to positive, while y stays negative. So the moment you see a coordinate like -4, 5, you instantly know that's quadrant 2. You don't even need to plot it. This little trick saves you real time once you start working with graphs at scale. Okay, this is the part most students miss. And once it clicks, calculus suddenly makes a lot more sense. A function is basically a machine. You feed it an input, it gives you back an output. So take a simple function, f of x equals x plus 1. Feed it 1, you get 2. Feed it 2, you get 3. Feed it 3, you get 4. Now here's the trick. Every input-output pair the function produces is actually a coordinate. The input is your x, the output is your y. So that pair becomes the point x, y on the plane. When you plot every possible input and its matching output, you get a collection of points, and that collection is the graph of the function. It's like a spreadsheet column being turned into a chart in Excel. Same data, just a visual shape instead of a list of numbers. The graph isn't decoration. It's a complete picture of what the function does for every value of x. And that's the lens calculus uses to study how things change. Let me show you the simplest kind of function, a linear one. Take f of x equals 2x plus 1. The name linear is a giveaway. When you graph it, you always get a perfectly straight line. Watch how it works. Plug in x equals -1, you get -1. Plug in 0, you get 1. Plug in 1, you get 3. And so on. Every pair becomes a point on the plane. Now here's the part that makes graphs so powerful. Once you plot just 2 of these points, you can draw the line that connects them. And that single line tells you the output for every possible x, not just the ones you calculated. That's an infinite amount of information packed into one clean shape. And the equation itself hides 2 clues about that line. The 2 in front of x is called the slope. It tells you how steeply the line rises. For every 1 step you move right on the x-axis, the line climbs 2 steps up. The +1 at the end is called the y-intercept. That's where the line crosses the y-axis, the value of y when x is 0. So just by looking at the equation, you already know how the line will sit on the plane before you draw a single point. Pretty neat, right? Now let's bend things a little. Take f of x equals x squared. This one's not linear, and you'll see why the moment we plot it. Plug in -3, you get 9. Plug in -2, you get 4. Plug in -1, you get 1. 0 gives you 0. and then it mirrors back up. 1 gives you 1, 2 gives you 4, 3 gives you 9. Notice something. The negative inputs and the positive inputs are giving you the same outputs. That's because squaring a negative number cancels the negative sign. Now when you plot all of these, you don't get a straight line anymore. You get a smooth curved U-shape. We call this a parabola. The lowest point of the curve, right at the origin, is called the vertex. And the curve is perfectly symmetric, folded along the y-axis, and the two halves match exactly. This is the big jump in calculus. Real-world things rarely change in straight lines. The path of a thrown ball, the way of video buffers, the growth of a savings account, they all curve. And calculus exists precisely to study that curvature, to measure how quickly things change at every single point on a curve like this. Which brings us to the why. So here's the payoff. Why did we spend a whole video on coordinate planes and graphs? Because everything in calculus is built on top of this picture. When you study limits, you're really asking, what value does the curve approach as x gets close to some point on this plane? When you study derivatives, you're measuring the slope of the curve at a single point. Basically, how steep is it right here versus right there? Look at this curve. At the bottom left, the curve is almost flat. Slow change. In the middle, it's tilting upward. Medium change. Near the top right, it's climbing fast. Rapid change. Calculus gives you the tools to measure exactly how much change is happening at every single point on a curve like this. And when you study integrals, you're calculating the area trapped between the curve and the x-axis, which turns out to be useful for everything from physics to economics to machine learning. None of that is possible without first being able to read the picture. Points become coordinates. Coordinates form curves. Curves represent functions. And the shape of those curves tells you the story of how something changes. That's the entire foundation. Master this, and the rest of calculus stops feeling like abstract symbols. It starts feeling like geometry you can actually see. And that's the foundation. You now know how to read a coordinate plane, how to plot points, how the 4 quadrants behave, and most importantly, how a function quietly turns into a graph you can see. This is the lens you'll use for every single topic in calculus from here on. In the next videos, we'll start using this foundation to dig into limits, derivatives, and integrals, the 3 big ideas that make calculus what it is. If this video helped things click, hit like, subscribe to Webronaq, and I'll see you in the next one. Take care.